In the last section, we spoke about some common runtime complexities. We're now going to continue by talking about some odds and ends around runtime complexity. So just some things I think you should really know about it. The first thing I want to discuss is big O notation. So big O is another way of referencing runtime complexity. So your interviewer, after you finish some algorithm, they might ask you, hey, what is the runtime complexity of your solution? They might also ask you, what is the big O of your solution? Either thing that they ask, they are both asking what is the efficiency of your solution? What is the runtime of your algorithm? Big O notation is a way of writing out this runtime complexity that is commonly seen in the academic world. So for example, linear runtime could be indicated by writing O, and it's called big O because it's literally a big O, of n. So if you see O of n like this, that indicates linear runtime. O of 1 would be constant, O of n squared would be quadratic. So essentially, when you start seeing these big O's with some kind of little equation inside of it, we're really still talking about these different runtimes over here. The term big O in general means something slightly different in the academic world, but in an interview setting, anytime you hear runtime complexity or big O notation or anything like that, they're always asking you what is the efficiency of your algorithm. Now the next thing I want to tell you about is some tips around identifying runtime complexity. So for identifying complexity, and remember, this is what you're going to be asked in an interview setting. For identifying this stuff, I've got good news and bad news. The good news is once you get some experience with it, it gets pretty easy. The bad news is that like many other things in the interviewing world, there's not some magic formula that you can just be given that 100% of the time always correctly identifies the runtime complexity of something. It's something where you have to have a little bit of experience, you have to look at some different algorithms and just get a sense of what's going on. There's really not a hard and fast rule of exactly how this stuff is done. So I'm going to give you some tips right here on some common complexities and how you can identify them. As we go through many other algorithms and solutions in this course, we will also spend some time to discuss their runtime complexity as well, so that you can start to develop that sense of what runtime complexity is and how to really determine it. So let's go through some of these really quickly. Again, I know it's really annoying when a presenter reads directly off a diagram, but I'll add some extra words in here on each of these. So the first one is, if you ever see yourself iterating through a simple for loop with like a single collection, great example of which would have been our reverse string algorithm back here. So we had a simple for loop, more or less, iterating over a fixed set of records, right? Like just these characters right here. Whenever you see that, chances are you have linear runtime, extremely likely. So simple for loop probably means you have linear runtime complexity. The next thing to keep in mind is, okay, well, if we are only iterating through, say, half a collection, like if we only look at half a string, does that mean that we are using a runtime of like n divided by 2? No, there's no such thing as like n divided by 2 or 1.5 times n or 2 times n or 3 times n in runtime complexity. Take any of those numbers, like any of those what we refer to as constants, and you always drop them out of the equation. So anytime you see a for loop iterating over a closed set of data, even if it stops early, even if it says, oh, I'm only going to iterate through like half this thing, it's still going to be a linear runtime. So always drop out those constants. Another thing to watch for is if you are iterating through two different collections of data. So imagine, for example, if we had said, okay, write an algorithm that reverses two different strings, reverse both of them in one function call. That would be an example of iteration over two different collections of data in two separate for loops. So you would have one for loop to reverse the first string and then one for loop to reverse the other string. So those would be two separate for loops. In that case, we would introduce an additional term into our runtime complexity. We would say something like that has runtime complexity of n plus m. So the n in this term right here is meant to indicate the runtime, the performance impact of the first string. And then we would introduce this second term right here to represent the second string. Because in theory, you could be passed a very, very short string for the first argument to your dual reverse function, and then a extremely, extremely long string for that second argument or that second string. And so we would want to separate those two out and say, okay, we are reversing two separate, completely different strings. One might be short, the other might be long, and so we would want to represent those separately. In general, this is not only applicable to two strings. Anytime you're iterating over or processing two completely different sets of data, you'll frequently see the runtime complexity split out to two separate terms. Now the next one is very closely related. If you ever see nested for loops, a nested for loop is like a big, oh, take a look at that right there. It's a big red flag. If you ever see nested for loops iterating over the same collection, so the same collection of records, very likely that you have quadratic runtime or n-squared complexity. And a great example of this was the stair algorithm and the steps algorithm right here. Here's the steps algorithm. So we had one for loop right here and a second one nested inside of it. Another great example of this was the pyramid algorithm that we put together. So here's pyramid. Here's the iterative solution right here. Oops. There we go. So here's the iterative solution, and we very clearly had one for loop where we iterated from 0 to some target number, and then inside of that we had another for loop that iterated from 0 to some upper bound up here. So anytime you see these nested for loops, huge red flag, extremely likely that you might have n-squared runtime. Very closely related to that again is if we have two nested for loops, but each one is iterating over a different collection of data, a different collection. In that case, just like we said a moment ago with two separate strings, we might have one string or one collection of data that's very short, and the other one might be very, very long. So that would no longer be n-squared because we have two different collections of data, and they might have different requirements or different lengths in each of them. And so we would reflect that as being n times m. Remember, that's not quite so different than n squared. Remember that n squared is simply n times n as well. So it's really the same thing here. We are just specifically saying, hey, there's this other set of data that is not related to n. It's called m, but still for every record in n, we have to also iterate through m. And so that would be an example of n times m complexity. Now the last two here are two that are great shortcuts to have, very close at hand. These are very, very commonly used. Anytime you ever see any requirement in a sorting or a problem for sorting, any requirement whatsoever, you can essentially just immediately assume that it's probably going to be n log n runtime. So every sort operation, the best runtime complexity we can have for sorting something is n log n. So if you have an algorithm where you have to sort something, chances are you will probably see a term like this inside there. Then the other thing to keep in mind is searching through a sorted array. So if you have an array of, say, numbers or a collection of anything that is sorted in some fashion and you have to search through it, chances are you have a log n runtime complexity from that operation. So anytime you see sorting or searching, you likely will have something related with one of these runtimes right here. So just something to keep in mind. Okay, so that is a quick list of big tips to watch out for when identifying runtime complexity. Again, this is something where you just got to have a little bit of experience. You got to do it. You have to be told, okay, here's the algorithm, here's what the runtime complexity is, and you have to develop your own feeling for how it actually works. It's not something where I can just give you, hey, here is the absolute, rule of thumb to use 100% of the time. That doesn't exist for this, unfortunately. I wish it did. Now, the very last thing I want to tell you about, kind of a last minute thing I'm going to throw in here, is space complexity. So we've been talking about runtime complexity, which is a reference to the performance of an algorithm in terms of processing power. Another thing that you might be asked in an interview setting is the space complexity of an algorithm. So space complexity is extremely similar to performance, but it is a reference to how much RAM or memory or space an algorithm needs to complete a given task. In general, you can really apply a lot of the same rules around runtime complexity to space complexity. Great examples of this would be something like reversing a string. In our case, for every additional character that we added into our input set, we had one additional character that we needed to return in the output set of data. And so the amount of memory that we spent was linear, because for every one additional character, we needed one additional element in our string to be added. Another good example of this would be the steps algorithm that we also looked at. So in this case, we had said that for each increment of the steps argument, we had to print out some number of additional items in our result set. So not only do we have to process more data, or we had to iterate through some loop more times, our result set also had significantly more entries inside of it for every record that was added in. And so this would be a great example of quadratic runtime for space complexity as well, because you can see very clearly right here, for 2, we had to produce 4 items, so 4 elements in memory. For 3, we needed 9 elements in memory, and for 4, we needed 16 elements in memory. Now, the space complexity and runtime complexity are not always going to be identical. In many cases, they might be very different. However, again, we'll see some examples of different space complexities over time. I will say that space complexity is less frequently asked in an interview setting than time complexity. So if you're going to spend any time doing any studying or anything like that, I really recommend pushing all of your time towards studying up on time complexity opposed to space. But honestly, once you understand one really well, usually you can pick up on the other pretty quickly as well. So just keep that in mind. Okay, so this has been a lot of discussion around runtime complexity, a lot. So let's continue in the next section. We're going to start looking at some more algorithms that start to get into this world of runtime complexity. So let's continue in the next section, and we'll start looking at some more complicated algorithms. So quick break, and I'll see you in a minute.